Equivalent resistance. There are two ways to add a second resistor to a circuit. You can add them in series, where all the charges must move through both resistors to get back to the negative terminal of the battery. You could also add them in parallel, where charges pass through either R1 or R2, but not both. Are the following sets of resistors in series or parallel? Well, here, the charges leave the battery, and then some of them will go that way, some of them will go that way, which means these are in parallel. However, here, all of the charges will go through R1, and then all of the charges will go through R2. So these are in series. Resistors in parallel do not have to be drawn in parallel lines. They just need to provide separate paths for the charges to get from the positive battery terminal to the negative terminal. Resistors in series only have one path for the charges to get from the positive battery terminal to the negative terminal. Resistors and voltage from batteries determine the current. Circuits can be redrawn as if there were only a single resistor and battery. By reducing the circuit this way, the circuit becomes easier to study. The process of reducing the resistors in a circuit is called finding the equivalent resistance. What happens to the current in the circuit to the right? The current passing through all parts of a series circuit is the same. The current leaving the battery is the same as the current going through each resistor. For example, I here is the same as I1, is the same as I2, so they are all equal. What happens to the voltage as the charges move around the circuit? Charges leave the battery with a certain amount of energy per charge, voltage. As they go through resistors, they use up some of this energy until they have zero energy by the time they get back to the battery. Therefore, the sum of the voltage drops across each of the resistors in a series circuit equals the voltage of the battery. So let's go through this. Charges leave the battery with a voltage of V. Then they're going to use up some of that voltage here, and then they will use up the rest of the voltage there, so that they return to the battery with no energy left, zero voltage. So here we start out with V voltage, then we're going to end up with V minus V1 voltage after this resistor. Finally, V minus V1 minus V2 will be zero once we get past the second resistor. So for series circuits, we know that the voltage drops through each resistor have to add up to the total voltage of the battery. And we also know Ohm's law. So V equals IR. So the voltage of the battery is IR. The voltage drop in the first resistor is I1R1. The voltage drop in the second resistor is I2R2. But we know that the current is the same everywhere in a series circuit, so therefore we can drop the subscripts after I1 and I2 since they're the same. They just become I. Now every term in this equation has an I in it, so we can divide the whole thing by I, and we get Req, the resistance of the entire circuit, is equal to R1 plus R2, etc. To find the equivalent resistance of a series circuit, add the resistance of all the resistors. If you add more resistors to a series circuit, the overall resistance increases. On the AP Physics 2 equation sheet, this relationship is expressed with a summation. We have R sub S, where S stands for series. And here, I starts at 1 and goes up to however many resistors you have that are in series. So the summation of R sub I would be, first we put in a 1 here, so R1 plus R2 plus R3, etc. This presentation generally refers to all equivalent resistances as Req. What is the equivalent resistance of this circuit? These resistors are in series, so we just add them together. Req equals R1 plus R2. R1 is 5 ohms, R2 is 7 ohms, therefore the equivalent resistance is 12 ohms. Here is another way that you could draw this same circuit in order to find the current leaving the battery. So you could represent this as one resistor with 12 ohms of resistance. Adding resistors in series always increases the equivalent resistance. What is the total current at any spot in the circuit? You can use Ohm's law on individual circuit components or on the entire circuit. Just make sure to plug in the appropriate numbers. Since we're finding the current going through the entire circuit, we're going to use Req and the voltage of the battery. So Ohm's law, I equals V over R. We're trying to find the current right here, the current leaving the battery. So therefore the voltage of the battery is 9. The equivalent resistance for the whole circuit is 12. Therefore the current going through the entire circuit is 0.75 amps. What is the voltage drop across R1? On previous slides, we found that the equivalent resistance was 12 ohms and the current going through the circuit was 0.75 amps. Now, the current is the same everywhere in the circuit. There's just one path all the way around, therefore that current is 0.75 amps going through this R1 here. So we can use Ohm's law on just R1. We just have to make sure that we plug in information for R1. So we rearrange Ohm's law. So remember, it's I equals V over R, so therefore V equals I times R. The voltage drop across 1 is going to be the current going through R1, which is 0.75 amps, times the resistance of R1, which is 5 ohms, giving us 3.75 volts. That means that of the 9 volts provided by the battery, 3.75 of those volts are being used up in R1. What is the voltage drop across R2? There are two strategies you can use. You can either do what we did on the last slide. You can just use Ohm's law for R2, which means instead of 5 ohms here, you put in 7 ohms, since this has a resistance of 7 ohms. Or you can think about it as every charge leaving this battery starts with 9 volts of energy. Each charge loses 3.75 of those volts here. Therefore, how much do they lose here? They use up the rest of it. So 3.75 plus 5.25 adds up to 9. So therefore, they lose 5.25 volts of energy in R2. What happens to the current in the circuit to the right? There are two possible routes or branches for charges to take. So all of the current comes this way, goes up this way, and then here, some of the current goes that way, the rest of the current goes that way. So the sum of the currents through each of the resistors in a parallel circuit equals the current of the battery. So in this example, the total current is going to be equal to I1 plus I2. Now, will those be the same? If those resistors are the same, then yes, the currents going through each branch would be the same, but not. If these are different resistances, then we will have to calculate the current going through each branch. What happens to the voltage as it moves around the circuit? The voltage across all of the resistors in a parallel circuit is the same. The charges will either drop their voltage across R1 or R2. They will start out with V voltage, then they're going to either go through R1 or R2. Regardless of which one they go through, they're going to lose all of that voltage. So V here, the voltage of the battery, is going to be equal to the voltage drop across R1 and equal to the voltage drop across R2. For parallel circuits, the current split between two branches adds up to the total current in the circuit. We can rewrite Ohm's law for this equation here because I equals V over R. Therefore, instead of total current I, we can write V over R, which this V would be the voltage of the battery, this R would be the equivalent resistance for the entire circuit. Set that equal to I1, which is going to be V1 over R1, and I2 is V2 over R2. Since the voltages are all the same, we can get rid of these subscripts here, and this will be the same V. Therefore, we can then factor it out and divide it from both sides. And we are left with this equation. 1 over the equivalent resistance for the entire circuit is going to be equal to 1 over R1 plus 1 over R2. On the AP Physics 2 equation sheet, this relationship is expressed with a summation, where R sub P stands for parallel, and I goes up to the number of resistors that are in series. So this is a summation here. So this is the same thing as this, where we have 1 over R1, then 2, 3, 4, and so on. This presentation generally refers to all equivalent resistances as R sub EQ. Adding more resistors in parallel will decrease the equivalent resistance of the circuit. Check the math out and you'll see it's true. A 6 ohm and a 3 ohm resistor in parallel result in a 2 ohm equivalent resistance. Conceptually, adding more resistors in parallel gives more paths for the electrons to flow. Hence, for a given electric potential, more current will flow, which indicates a smaller resistance. The equivalent resistance in the parallel circuit will always be less than the smallest resistance. For example, when 2 resistors of 1 ohm and 1,000 ohms are connected in parallel, the net resistance is less than 1 ohm. 4 resistors with values of 20 ohms each are connected in parallel as shown in the circuit below. What is the equivalent resistance of the circuit? Alright, so since they're all in parallel, we can just plug all of the resistances into this equation here. So 1 over 20 plus 1 over 20 plus 1 over 20 plus 1 over 20 is 4 over 20, but that's 1 over R. So then we flip the whole equation over, or you can do cross multiplication, right? 4 REQ equals 1 times 20. Therefore, R equals 5 ohms. There is a shortcut. When there are resistors with the same value that are connected in parallel, the equivalent resistance can be found by dividing the individual resistance by the number of resistors. 2 resistors with values of 12 ohms and 4 ohms are connected in parallel, as shown in the circuit below. What is the equivalent resistance of the circuit? All right, let's use our equation. 1 over REQ equals 1 over R1 plus 1 over R2. So we plug in 12 and 4. We need a common denominator here, which 1 over 4 becomes 3 over 12. 1 over 12 plus 3 over 12 is 4 over 12. Then we flip it over and we get 3 ohms. There is a shortcut. When there's 2 resistors connected in parallel, the equivalent resistance can be found by dividing the product of the 2 resistances by their sum. So in this case, that would be 12 times 4 divided by 12 plus 4, and that also gives you 3 ohms. Find the equivalent resistance of this circuit. We need to work from the inside out. We can't just add 3 ohms to 4 ohms because this 3 ohms is trapped by the 6 ohm, right? These are closer together. They need to be solved first. So first, we will figure out the equivalent resistance of these 2 resistors, then we'll just add the 4 ohms at the end. So 3 ohms and 6 ohms are in parallel, so that has an equivalent resistance of 2 ohms. So we have 2 ohms here. We're just going to add it to 4 ohms to get a total equivalent resistance of 6 ohms. Find the equivalent resistance of this circuit. All right, once again, we need to work from the inside out. Since the 3 ohm and 1 ohm resistor are in series right next to each other, let's find their equivalent resistance first and then solve for this parallel resistance. So 3 ohm plus 1 ohm is 4 ohms, and then we just add the 2 ohm resistor in parallel. So first we add them in series to get 4 ohms up top. Then we have a 4 ohm resistor and a 2 ohm resistor in parallel. So we use our parallel equation, and we see that our total overall equivalent resistance is 4/3 ohms. Find the equivalent resistance of this circuit. We need to work from the inside out. This is a three-step process. So first, we can add these two resistors that are in series right next to each other. Then we're going to have two resistors in parallel. Finally, we will add this resistor, which is then in series. So first, we add these together. 2 plus 3 is 5. Then we have a 5 ohm resistance over here in parallel to a 4 ohm resistance. We add those using our parallel equation and we get 20/9 ohms. Finally, we have a 1 ohm resistor over here that we have to add in series. And so 20/9 plus 1 gives us 29/9 ohms.